Help me get this helmet off. Oh, jeez. Okay, there we go. All right, reporting to you live again from the moon again. I've got really nothing else to say about that. What we're going to do is continue from sort of what we were talking about last time and fulfill a promise from a few videos ago where we're going to talk more about the eigenvalue and eigenvector problem here. And we're going to do it a little bit in general. I'm going to show some examples and some like ways to think about it. And yeah, we'll go from there. We're going to be sticking to 2D as always. A lot of this is more generalizable to higher dimensions. That's fine. That is neither here nor there. Okay. So to refresh us, I want to be thinking about a system of differential equations like x prime equals ax plus by and y prime equals cx plus dy. Okay. Now, by defining some vector u to contain the elements x and y, so u varies with time, and a coefficient matrix A, which has elements A, B, C, and D in them, okay, we can rewrite our differential equation like u prime equals A u, which is now vector valued. So it's like, it's kind of one-dimensional, but it's like one vector, so it's 2D in the way that we like to think about it, okay? And what we're looking for is straight line solutions. So that means what we're doing is we're looking for objects like this. Now, we have covered this ad nauseum in previous videos here, okay? But what I want to do now is work my way through doing this a little bit, okay? So let's go ahead and start with an example. Here's example 1, and I'll have the matrix 1, 2, 1, 0. So if you're following along right now, what is the system of differential equations that corresponds to this coefficient matrix? Take a second and write it down. Okay, if you get it written down, hopefully you have x prime equals x plus 2y, and y prime equals x. Okay, not decoupled, it's perfectly coupled here. But so this is the system that we're talking about right here. All right, if I want to find those lambdas, my eigenvalues, then I'm looking at the determinant of, I take this coefficient matrix and I subtract lambda from all my diagonal elements. And the determinant gives me 1 minus lambda times negative lambda minus 1 times 2, all that equals 0. And I blow that out and I get lambda squared minus lambda minus 2. And that should equal 0. Okay? By wanting this to equal 0, the reason why we have this determinant equal 0 is because we want, let me just clue you in on why here I want it to be equal to 0. I want 1 minus lambda, 2, 1 negative lambda times v1, v2, which equals the 0 vector. I want this to have a solution other than just the v1 and v2's equaling 0. So the matrix, in a way, has to behave like the number 0. And the way that we kind of figure out how matrices behave like numbers is we take their determinant. All right. And so we're left with finding these lambdas. And what we get from here is lambda equals 2 or negative 1. You can work it out. Okay. So now these are my eigenvalues, 2 and negative 1. Now what we're left to do is to figure out what the eigenvectors are that correspond to them. So for lambda equals 2, this matrix right here becomes negative 1, 2, 1, negative 2. And I'm multiplying that by v1, v2, and I'm setting that equal to the 0 vector. Now, what you should be able to see here plain as day, which is true for all these eigenvector problems right here, is, that's a little too wide, undo, is that the top row and the bottom row are dependent on one another. In other words, they don't tell different stories. Okay, if you look at the top row and you multiply it by -1, you get exactly the bottom row there. Ignore the fact that V1 and V2s are there. I was really just referring to those rows. Anyway, so it's a redundant system, so you only have to pick one of them to write down. So I'm going to use the first one, -V1 plus 2V2 equals 0. And this is what I'm left to solve. Now, when you're left to kind of decide what goes on here, you have one equation, two unknowns. You can always pick a value for one of them and continue on. Never pick 0, because 0 has no information in it. So the value I usually pick is the number 1. So if I let V1 equal 1, then V2 is going to equal -1/2. And so the vector that corresponds to this is 1, -1/2. Now, there's also this thing where, did I do that right? No, whoops, that negative sign is not there. There's also a thing where I don't like writing fractions, mostly because they're small and messy, okay? So what I could have also done to anticipate this, let's go ahead and change my color here to denote this. I could have let V1 equal 2. Then if V1 was equal 2, I'd have -2 plus 2V2 equals 0, which now makes V2 equal to 1. And so the eigenvector 2, 1 would work. And so you might be like, well, wait a minute. Now I can have two different eigenvectors for the same eigenvalue. What's happening here? Let's take a little aside, okay? If AV is equivalent to lambda V, where lambda is one of my eigenvalues and V is my eigenvector, okay, I can multiply both sides of this equation by any number. Let's pick C, okay? So CAV equals C lambda V. And I'm multiplying them both on the left because with matrices and vectors, you're just going to be careful. Now, the C is a scalar, so I can move it about, and I can rewrite my left-hand side as A times the quantity CV, and my right-hand side is lambda times the quantity CV. And CV is basically just another vector W, in which case, then AW equals lambda W. Holy crap, W is also an eigenvector. So the moral of this story is any multiple of an eigenvector is also, there's an S there, an eigenvector. So once you have your vector, whether or not you chose cleverly at first or not, why did it go all the way to the top? So if I didn't choose cleverly at first and I get a 1, 1/2, or if I did and I get a 2, 1, doesn't matter. Just go ahead and pick the form that you like the best. Okay. All right. So the next eigenvalue, lambda equals, what was it? -1, I think. Sure, we'll go with that. All right. So my matrix is 1 minus lambda, 2, 1, and negative lambda. Let's go ahead and plug that lambda in there. And I get 2. Awesome. 2, 1, 1. You can definitely see the first row there is just 2 times the bottom row. So they're dependent. They don't contain any different information. Putting this into the problem that I need to solve, I get V1 plus V2 equals 0. So it doesn't matter. If I choose V1 equals 1, then V2 is going to equal -1. And so my vector here is 1, -1. So to sum up what you just found, okay, you found an eigenvalue of 2 paired with an eigenvector of 2, 1, and an eigenvalue of -1, which is paired with the eigenvector 1, -1. And I'll show you guys how to use those in the next video, okay? I wanted to do one more where we dealt with complex values, because complex has been coming up. It's how we got sines and cosines. And I want to make sure that when you see it for the first time, you're not like, oh, holy shit, what am I supposed to do? Okay. So this other example here, which is really long, okay, is, oh, nuts. I don't want to start this example yet. I wanted to do one last thing. I'm so sorry. Okay, we got these, whoa, these pairings right here. So what does this mean in terms of the differential equation that we decided we were solving for, which is this system right here? Well, what it means is that for x prime equals x plus 2y, and y prime equals x, that we have solutions u of the form c1. Can you let me write a c? There we go. v1 e to the lambda 1t plus c2 v2 e to the lambda 2t. And so if I just want to write that out in all of its ugly glory, there's my first eigenvector. There's the corresponding eigenvalue to it. Here's my second eigenvector. And here is the second eigenvalue corresponding to it. That is a solution in vector form. If you just read off the top, that's what x of t equals. And if you just read off the bottom, I meant to include all that e stuff. It's so ugly. That's what y equals. X equals 2c1 e to the 2t plus c2 e to the minus t, and y equals c1 e to the 2t plus negative c2 e to the negative t. And you'll notice that I have numbers in front of these coefficients, and you might, why don't you just squish them in? Because it's important information that whatever the coefficient is in front of this first term in the x solution is twice that what's in the y solution. And it's important that whatever number is in front of the second part of the x solution, we need negative that in the y. So it's important to leave those numbers. I apparently have to stop this video. I'm going to do a short one on complex eigenvalues and eigenvectors in about half an hour when I let this thing charge. Okay, bye-bye.